second edition of our Advanced Kotlin series, and we're really thrilled to have you with us today. We've also got a great speaker lined up for you today. This is going to be a little Codelab style. I'll get into that, what that means, but we're really excited about today's droidCon online webinar. Let me just go through a couple of housekeeping items in case this is your first time being here at a droidCon online webinar. One of the first things you're going to want to do is head over to slido.com and enter this room code. What that will allow you to do is during the session, you can ask questions. So type in your questions there, and what Slido will allow us to do is prioritize. So if you see a question that you think would be, you wanted to ask the same question, or if it's a question you think is really important, give it a thumbs up, vote it, it'll slide to the top. So when David does the Q&A today, we'll be able to get through the most important questions first. In your little interface on the right here at GoToWebinar, you'll see a chat window. In the chat window, we'll be sharing some links with you today throughout the presentation, but in the chat window, you'll also find a unique URL as well that Uli will be sending over to you in just a moment. That'll give you a direct link to the Slido room where you can ask Q&A. Speaking about Q&A today, one difference between this and some of our previous webinars is that we have a single speaker today. We wanted to get more in depth and give you some more hands-on experience with the things we're talking about today. And so we've got one speaker. It's going to go for a little longer, about an hour, but David is going to break this up about halfway through. We'll do one Q&A session, and during the second half, after he's finished with this presentation, we'll do another. So if you have some questions that you want answered, you've got a chance during the midway point to ask some things, and at the end as well. So make sure you're paying attention to Slido and getting all your questions put into there. As you know, the videos are released in the next day or so. Immediately after here, they're all transcripted and searchable, and you can go to droidcon.com to find all the videos from this particular webinar on our Advanced Kotlin series, but everything else that we've done on droidCon Online. We've had part of our Jetpack series, we've done a multi-platform series here, and so we've got a lot of content there for you to check out. We're also wanted to remind you, coming up next on June 11th is part 2 of our Jetpack series. We had a great introduction to Jetpack and some of the great features and some great speakers on our first series. So come, make sure you register online for the June 11th Jetpack series part 2. Our speaker today is David Greenhalgh. Anybody who's Welsh, it will be totally intuitive that it's Greenhalgh. Anybody who's not Welsh will wonder how we got that pronunciation, but we're happy to have David with us here today and doing a Codelab style presentation, Intro to Channels and Flows. This was one of the most sought after and popular Codelabs at KotlinConf 2019. So we're excited to have David with us here today. He's going to be excellent. We are really happy to partner with Big Nerd Ranch on a lot of content that happens at droidcons, and particularly in the webinar. Brian Gardner was a speaker on Jetpack Compose in our first. We wanted to let you know about a few workshops, some more in-depth workshops coming up from Big Nerd Ranch in June and July. We'll push out this discount code. It's obviously going to be too long for you to write down now, but for all of our droidcon community and for those of you taking part in the webinars, we've worked out a little deal with Big Nerd Ranch to get you a discount on some of those workshops in the event that you're wanting to dive a little bit deeper into some things. So that's what we've got coming up for you today. We're excited to have you here. I'm going to turn the time back over to David now. That's who you're all here to see. So I'm going to just make sure that he is our speaker. He's set up. I'm going to turn off my camera, and you should be able to see David's slides momentarily. So David, feel free to take it away.
Hey there, thank you, Greg. Thank you for that generous introduction. Greg mentioned KotlinConf 2019, and that was the first time that we got out there in front of people to talk about channels and flows. And the reason why I wanted to talk about them today is in part because of how popular of a topic this seems to be. We're kind of at an inflection point at this point where people are comfortable with RxJava, they're comfortable with the concept of streams in their Android applications, and they're maybe looking to take the next step. They want something that's backed by coroutines maybe, they just want to learn more. And so this has been a topic that a lot of people have been asking us about. So that's what we're going to talk about today. Let me go ahead and get this slideshow going. Well, all right, can we still see my slides? We're all good? Okay. So again, I'm David Greenhalgh. I'm an Android team manager and instructor at Big Nerd Ranch. If you're not familiar with Big Nerd Ranch, people oftentimes know us for the books that we write, but a lot of the work that we do is also in training and consulting. So if you have an app idea that you want built out, we can help you with that. You'll also find us out teaching classes with this sort of material. iOS material, web material, design now, and I'm mostly involved on the Android side there. Today, as Greg mentioned, we're going to have a two-part session. We're going to start out with an introduction, or maybe for you, it's a reintroduction to coroutines. From there, we'll dive into channels. The reason why we're kind of starting with that foundation in coroutines again is maybe coroutines are new to you. Maybe you're happy with RxJava, you're happy with your current threading strategy, and you've heard about coroutines, but really just haven't taken the jump into them yet. Well, we'll give you everything that you need in these first, let's say, 15 or 20 minutes or so to know really how channels and flows work under the hood and how you can most efficiently work with channels and flows. So that'll be our first half, that introduction or maybe a reintroduction to coroutines, focusing on the parts of the coroutines API that are most important for writing channels and working with flows. We'll have a Q&A session where we can talk about those topics, and then we'll dive into flows, and particularly flows as they relate to RxJava. Okay, you'll often see them compared one-to-one. That's an apt comparison in some ways, and in other ways, you can just get away with using traditional suspending functions. So we'll spend the second half of that flows 30 minutes talking about how flows relate to RxJava and how their APIs might be similar or dissimilar as it may be. So coroutines, in a nutshell, they spread work across multiple threads. So they give us tools to take long-running work, and rather than blocking a thread doing that long-running work, we can suspend that thread instead. So we're not taking up an entire thread to wait for our work to be done. The advantage of coroutines is that thinking in this way, well, it can be quite efficient. If we had 1,000 pieces of work that we wanted to do in parallel, we might need 1,000 threads to do that work before. But with coroutines, rather than blocking each of those threads individually, if we suspend those threads, we could maybe get that work done in 15, 20, maybe even less threads. All right, it's indeterminate. It depends on your system specs, the type of work that's being done, etc. So we can dramatically reduce the number of threads that it takes to do concurrent work using coroutines. And that's our key advantage. Now, coroutines, you might have heard of them for a while. They were first experimental in Kotlin 1.1. The coroutines API has changed fairly significantly over time, and they just hit stable in Kotlin 1.3. A lot of the stuff that we'll talk about, particularly around flows, especially later in the talk, is still experimental, right? It's still being ideated or iterated upon, and so you'll sometimes see the linter warn you that you're using some experimental coroutines API. But overall, the APIs for coroutines are stable, and anything that's experimental is mostly stable. And I'll call out some of the cases in which things are still moving. So coroutines, the idea has been around for a while, fairly new in Kotlin. The idea of coroutines itself, dates back to 1958 by Melvin Conway when he first mentioned this idea of a coroutine. In essence, our coroutines relate to a couple other concurrency solutions that we have on Android and similar Java frameworks. Threads, futures, promises. Maybe you use something maybe a little bulkier like an async task. Okay, these are all other solutions that we can accomplish what we want to using coroutines and maybe replace some of these other solutions or integrate with some of these other solutions. Now, I mentioned callbacks here, and we don't always think of callbacks as a concurrency solution, right? But in essence, callbacks are a way for us to receive a ping when some work is done, right? Maybe we fire off a request and we want to get a result back at a later point in time. That callback syntax fits really nicely in with the sort of deferred execution syntax that we're looking for. But there is a problem with that callback syntax, and that's how we'll introduce some of the problems that coroutine solves outside of that efficiency versus threads that I mentioned before. So let's say that we make a call to a function called fetch character data. We're getting some information about a character of a game, right? So we call fetch character data, and in that callback, we'll receive that character data back at some later point in time. Now, this callback syntax has nothing to do with the concurrency. It's not prescriptive about any of that, but it's just the syntax that we're looking at here. So we call fetch character data, we get some character data back later, and now we have that character data and we want to do something with it. Maybe we want to get a map for that character so we can learn more about where that character lives. Then once we get that map data back, maybe we want to cache that map for that character. You can see very quickly our code gets wider, right? We find ourselves in what is sometimes referred to as like callback hell, because we're chaining these callbacks one after another. And syntactically, this is what coroutines tries to solve for us. And the way that it does that is via suspending functions. So you can append the suspend modifier onto the front of a function to make it a suspending function. And within that function, you do some sort of heavy lifting. Maybe it's a web request. Maybe you're reading some data from the disk, and that's going to take a while to do. Okay, that's what a suspending function is really good for. So we'll throw the suspend modifier onto a function in order to declare it as suspending. Now, something that we have to be, I'll say, specific about when calling into suspending functions, we need to call them from a coroutine. Okay, a suspending function has to be called from a coroutine, and the way that we create a coroutine is via a coroutine builder, right? There are a couple different examples of coroutine builders out there. Launch is a really common one. You may be familiar with async and await. Maybe you have a JavaScript background, and async is another coroutine builder here. But let's just talk about launch for this session. So launch creates a coroutine and fires it off. Now, in this case, launch, this coroutine is being launched into something called global scope that we'll talk about in a second here. But note that within this coroutine, within this launch builder, we just call fetch character data. We get some character data back. And then on the very next line, imperatively, we just call display character data. We work with that character data that we received on the line above. Now, fetch character data could suspend its thread for a while, right? And display character data won't be called until that character data is back. All right, so that's the syntactic problem that we're trying to solve with coroutines, right? Avoid all of these callbacks and call something that looks a bit more natural. So I talked about the scope here, this global scope. Now, launch and really any coroutine builder returns a job. Okay, this job gives you some more information about the coroutine. So whether the coroutine is active, whether it's already completed, whether it was maybe canceled, and maybe there's a reason it was canceled because some exception that was thrown. These are all stored on the job object, okay? And that's returned out of that launch coroutine builder. So why would we manage, why do we care about a job? Why do we care about whether a coroutine is active or canceled? Well, these coroutines, we have to manage them like resources. Okay, let's say we launch coroutines, we hold on to some resources, and then we navigate away from the screen in our application. Well, we want to clean up after ourselves. So that's why we have to think about something called structured concurrency. In this example, we are just launching a coroutine into global scope, right? It's a bunch of coroutines all together, all unmanaged, and they're not bound to the lifecycle of any particular resource. And that's a problem because we can't manage them as a scope. So each coroutine scope has a context, okay? A coroutine context is comprised of a dispatcher and a job, and there are a couple dispatchers built into the coroutines API that I added for you out of the box. Let's first talk about default. All right, this is, of course, the default dispatcher. This is what you get if you generally don't specify something and your coroutine scope doesn't specify something, you get the default dispatcher. This is good for CPU-bound work, long-running work. There's also I/O. I/O functions a bit like default, but it has a larger thread pool and is generally better for file I/O operations. That larger thread pool means that this pattern is advantageous for doing work that suspends a lot and you're jumping between different threads. So default and I/O are two that you're going to use in the background really often. There's also main. Now main varies depending on where your coroutine is being called. Because we're talking about Android here, this is generally going to be the main thread on Android, the UI thread. And it's something similar on JavaFX or Swing. Now, if you're in Kotlin JS or Kotlin native, main is just going to point to dispatchers.default. And I should note that a lot of coroutine work is farthest along on Kotlin JVM right now. There isn't feature parity on Kotlin native yet. And most of what we're talking about here is going to apply most directly to Kotlin JVM. So default and I/O, good for background work. Default is better for CPU bound. I/O is better for accessing the disks, etc. Main corresponds to your main thread on Android. And lastly, unconfined is just kind of get this coroutine going immediately on the current thread, and we'll worry about it later. It's less often that you see unconfined used. So those are our different dispatchers. So let's come back to this idea of structured concurrency. We launch coroutines intentionally into coroutine scopes. Coroutine scopes have, they have a pool of jobs that are managed, okay? So we manage scopes like resources, and oftentimes in Android, we tie coroutine scopes to things that behave like resources, things that have life cycles, like view models, or there's a scope called lifecycle scope that's provided in Android's coroutine extensions, okay? So we manage coroutines collectively because we need to clean up after ourselves. And this is a really important idea that defines and motivates a bit of how channels and flows especially work, right? We get a lot of syntax for free in flows because flows kind of opt into this structured concurrency pattern. Now, this is a lot of new vocabulary if you're new to coroutines, but the tools that are out there actually help give you a really straightforward, really simple syntax. An example that I'll call out specifically is the new or newish view model scope in the Android Jetpack view model. Okay, view model scope is a coroutine scope that is scoped to your view model. So the syntax that you get is something like this. Let's say that we have a new character view model with a function called fetch new character. Now, fetch new character goes out into the character repository, fetches a character. Maybe it's from the web, maybe it's from the disk. It ultimately doesn't matter to the view model itself. You're just going to get a new character, okay? And when it's done, it'll send that character over to live data, and you're good to go. Now, view model scope is the really important part here. You'll note that in that example, I talked a lot about going to a repository. I talked about live data a bit, but very little of the syntax here actually has to do with coroutine, structured concurrency, any of that. And that's because that syntax is deceptively simple. All that we have to do is call viewModelScope.launch, and we'll launch a coroutine into this existing view model scope. Now, view model scope is cleaned up when your view model is cleaned up, and you're good to go. It's works similarly to maybe you're familiar with like autodispose from RX or something like that. So for all of that work that we just did, it results in a very, very simple syntax like this. And that is your crash course in coroutines, okay? Lots of what you do is actually made simpler by extensions to frameworks that you're maybe already using, like Room or Retrofit or some of the newer Android X libraries, view model as an example. But you can always build your own if you want to dig a little bit deeper or have some more, I'll say, custom implementation. So that was our recap or reintroduction, maybe just an introduction, and that's all right, to coroutines. Let's talk about channels. Now, the example that I just showed off, I'll step back here. From a view model, we're launching a coroutine, and that coroutine goes out into a repository object, right? And that repository object, maybe makes a web request or something like that, and just returns it directly back to the view model. And many of your cases in which you're using coroutines are going to be, well, they're going to follow that straightforward pattern. All right, we make a request and data flows back to us, right, at a later point in time. But sometimes the work that we do is a bit more complicated. And as you become a bit more comfortable with coroutines, maybe you want to branch out and have your coroutines talk to each other, right? Communicate between coroutines. That's what channels are going to do for us. They give us a consistent way to communicate between coroutines, okay? Now channels can be hot, and they have this simple send receive syntax that's kind of like a publisher consumer model. There are a couple different basic types of channels that we're going to cover here. There's a send channel that allows you to push emissions out onto a stream, out into a channel. There's a receive channel that allows you to receive transmissions. And then there's just this class called channel, and channel implements both send and receive. It can do both things. So if you're familiar with RxJava, this actually behaves fairly similar to a subject. It's a pretty close analog. So if we want to define a channel, if we want to define a stream that multiple coroutines can communicate through, all that we need to do is call the channel constructor. Now here we're defining a number channel. It's a channel that's going to hold emissions of the type integer, okay? Now from a coroutine, we can send emissions out onto that channel using the send function. So here we're just sending the numbers 0 through 9 out into that number channel. So we do so from one coroutine, and then maybe from another coroutine, we want to receive those emissions. So here we reference that number channel, and we call a method called receive. Now receive is going to take an individual emission out of that stream. Now, one of the cool things about channels is they have an iterator included in their implementation. So if we want to, and we just want to iterate through all of the emissions in the stream, we can do so using this familiar for loop syntax. So here, if we wanted to print out each number that was sent into the number channel, all that we need to do is use a for loop here, and for each number, which each number is an emission, we want to print it out. And under the hood, this for loop in that iterator implementation, it's receiving each element in the channel. Now, one important thing is that when we're done sending emissions out into a channel, we want to clean up after ourselves. We want to close up that resource when we're done. So whenever we're done sending, we want to call close when we're done. So that's the fundamentals of a channel. All right, we send things out into the channel. We receive those emissions later on when we're ready to process them. But there are a couple different patterns that we can get into that define how a channel behaves. The default implementation, and kind of what we just talked about there, was a rendezvous channel. Essentially what a rendezvous channel does is when you send emissions out into a channel, until they're received, any further sending into that channel is suspended, okay? Send is actually a suspend function. So until we call receive on the consumer side, any sort of publisher is suspended for the time being, right? And this means that we can using a fairly straightforward syntax, wait for any future, I'll say, consumers to be ready to process the work that we're pushing out into that stream. So rendezvous is the default channel pattern, and that's what you get when you just call the channel constructor directly like we did, with no arguments, nothing like that. Now, a couple other channel patterns. Channels can also have a buffer. Okay? If we want to, we can explicitly define a buffer for our channel. So let's say that we want to hold 4 numbers in our number channel at a time and no more. We can specify a buffer size of 4. Okay? Now, what happens when we try and send a 5th number into that number channel before the that first number is processed, is consumed? Well, it's just going to suspend. The sender suspends just like it did for a rendezvous channel. All right, so maybe we want to be explicit about the size of our buffer and manage how much data we're sending into a channel at once. A buffered channel is a perfect way to do so. Then there's a conflated channel. A conflated channel is pretty interesting. It explicitly has a buffer size of 1, and rather than suspending the upstream publisher, that conflated channel will just overwrite any element that's held in that channel before it's been consumed. Okay, so a conflated channel has a buffer size of 1, and it doesn't suspend that publisher upstream. Rather, it just overwrites the emission held in the channel. Lastly, and maybe the most fun if you're playing fast and loose with it, is the unlimited channel. The unlimited channel just takes things until it runs out of memory. So I haven't tested a whole lot of unlimited channels, and I'm not sure what sort of bounds it would take to run out of memory, but you can maybe try it on your machine if you'd like. So by default, rendezvous channels, the default behavior. Buffered and conflated channels provide some pretty interesting ways to manage what goes into your channel. And then the unlimited channel is can be fun, but can be risky as well. So that's a look at coroutines and channels. Now, before we get into flows, I think we did okay on time here. It's 11:27. Are there any questions about coroutines or channels?
Yeah, David, we have a few questions. I'm going to change Uli over to be our moderator, and he should be able to share the screen with you so that you'll be able to see what questions came up.
Perfect.
Okay, we're just waiting for Uli to share his screen. There we go. So David, feel free to read the top question, and then we'll go from there.
For sure. Now, actually, I want to jump down to the third question because it seems like I could be a bit more clear about the rendezvous pattern. And then I'll circle back to the top question, which is about some real world examples. So rendezvous channels are the default channel implementation. And I'll jump back here to how we define a channel. We just define a channel using the, am I screen sharing or, oh, that's Uli. So rendezvous channels are the default implementation. As we send emissions out into that channel stream, those emissions have to be consumed, right? And they're consumed using either like a for loop using its iterator or using a call to a method called receive, okay? So as we send more and more data out into that channel, that consumer actually has to process that data somehow, okay? Otherwise, we're really not, we're not making use of the emissions that we're sending out into the channel if we're just kind of like firing them out to the channel and then they're never actually processed. So what a rendezvous channel does is it essentially just it suspends that producer until the consumer can then process that data. And once that consumer is done processing that data, the next emission in that stream will be pulled out by the consumer. That producer upstream will be unsuspended, right? And a new emission will come into that stream, okay? So using the underlying, I'll say, essentially using the way that coroutines work and the way that suspending functions work, we get this relatively complex interaction model with a really simple syntax like the one that we saw with that number channel example, right? That channel constructor. Now, real life examples, real life situations of when to use some of these different channels or channel patterns in general. This is a bit of a tricky one. I would say rendezvous channels are great for just communicating between coroutines. I would say rendezvous and buffer channels are probably the most straightforward way to do that. Beyond that, I don't use a whole lot of unlimited channels in production, but conflated channels might be useful if you have several receivers and they all want to get the most up-to-date emission, right? The latest emission on a channel. Now that's one reason why we might use channels versus something like flow. And it's something that I didn't explicitly mention before. A channel is a stream that multiple coroutines can communicate through. And that doesn't just mean one producer and one consumer. It could mean that your channel, multiple producers are pushing emissions onto that channel. And it could also mean that multiple coroutines are paying attention to the results, right? Multiple coroutines are consuming that one single channel. So that's where channels are most useful. I will say, as we get to the end of the talk on flows, we'll talk a bit about the future of this sort of development. And really, the spoiler is that a lot of the functionality that we find in channels, especially classes like broadcast channel, conflated broadcast channel, that's going to be, or it looks like it's going to be replaced by flows in the future. So what are the pros and cons of flows and channels versus RxJava? Would you convert from RxJava to flows and channels? That's precisely what we're going to talk about in the following 30 minutes. I'll say a bit of a look forward there. It of course depends on your existing code base, but if I were starting a new greenfield project, 100% Kotlin, and a team that was already really familiar with Kotlin, comfortable with coroutines, all of that, I would opt for flows and channels over RxJava. But of course, that depends on your existing code base. How much Kotlin is it? How much Java is in there? Are you already familiar with RxJava? Have you invested in teaching your team RxJava, etc.? But we'll get into more of that in the following 30 minutes. What sort of coroutine scope should I use if I want to start one on leaving a fragment with a fire and forget mentality? Interesting. Now, this isn't something I've done a whole lot of, but if you're just kind of trying to fire and forget, then maybe you'd be okay using global scope. But if you're firing something away when you leave a fragment, you would want that coroutine to be scoped to somewhere, right? Maybe you're navigating away from a fragment to another fragment hosted by some single activity. You might want to use a lifecycle scope that's scoped to that hosting activity. That would be my best example. I don't know if I could explicitly recommend just kind of like firing a coroutine, leaving it unmanaged, and going from there. Can you use flows and channels for polling an API? Yes. So one thing that we'll talk about with flows is that they have an API filled with operators, just like RxJava does. Now, those operators include some polling operators, or you can create your own. Right. So if you were to poll using flows, yes, there are ways to do so. Also, channels have a pretty, I'll say a pretty apt channel builder called Produce that is good for that sort of work as well, where you can produce on some cadence. Maybe you want to pull an API once every 10 seconds. You can hit that API, delay for 10 seconds, hit that API again from within the channel producer. So is Kotlin dispatchers.io optimizer? I'm going to go with optimized for Android. As far as the particular optimizations under the hood, I'm not sure of any, but that doesn't mean that there aren't any. I'm just not familiar with them. RxJava versus channels. What is channels RxJava equivalent? That would be something like a behavior subject. And for me personally, one of the things that I mentioned in the wrap up is kind of looking back at channels versus flows and what the differences are. I think one key takeaway here is that we'll talk more about flows in part because I'm a biased author and I use flows more often. But also because I tend to find flows a bit more useful, just like I tend to find observable sources like observable and flowable more useful, or I use them more often than I do subjects. So yeah, subject would be, I think, the closest comparison with channels. Is it relevant in coroutines to have IO and default? This is a good question. It's a pretty common question. And really the answer is that under the hood, it's a slight optimization, right? There are some subtle differences there, but in how the dispatcher thread pool for default versus IO works. In dispatcher's default, essentially your thread pool is bound to the number of cores in your CPU. And in dispatchers.io, there's less of that bounding. So you can end up with a larger thread pool. Now, what that means for you when you're writing coroutines, if you're not going to be switching threads a whole lot, right? If you have some CPU bound work that's just going to run and run and run, and you're not switching back and forth between suspended threads, well then dispatcher's default makes sense. But if you are jumping through coroutines, if you're doing a little bit of work that's dependent on some other piece of work and jumping between threads a whole lot, that larger thread pool can be advantageous for you. So it's, depending on the sort of work you're doing, it might not show up every single day in a profiler, right? You might not drop a frame in your Android application because you use one dispatcher over the other. But if you are doing some really intensive work, that sort of thing can add up over time. And once you understand the difference between the two and you establish those patterns, kind of in your mental model, it can just be easier to opt into each one when you're doing that specific type of work. Does a rendezvous channel work like Rx when data isn't published to the stream unless an observer subscribes to it? Now, a rendezvous channel, when data is pushed into the stream, right, when you call send on a rendezvous channel, that send is a suspend function, right? So until that receive function is called, that publisher is actually suspended. So yes, there are absolutely some similarities there, but explicitly, most channel implementations are hot. We'll talk about how flows are cold here in a second and the subtle differences between the two, but you're on the right track there, yes. How can I pause a coroutine in on pause and resume its execution in on resume? Now, we talked about the fundamentals of coroutines, right? And how rather than just launching our coroutine into a global scope where it's unmanaged and can, maybe keep your fragments, keep your activities alive for long periods of time, well, we want to manage them I'll say as scopes, right? We're not managing coroutines individually, we're managing them as scopes. So in this case, if you wanted to pause a coroutine on pause and then resume and on resume, you would want to create a coroutine scope that had that sort of logic coded into the coroutine scope itself, okay? I highlighted view model scope as a common pattern. And highlighted the fact that some of the tools that you use, like Room or Retrofit, might have this sort of logic already built in. So you might be able to get away with everything that you want using something like lifecycle scope. But if you do want to codify really, I'll say, specific granular details into how your coroutines are launched, into how your coroutines are canceled, and how all of that allocation works, then creating a custom coroutine scope is the strategy for you. So we're at 1140. Should we dive into flows?
Why don't we dive into flows? Let me get you changed back here as our moderator here, and then you should be able to share your screen again, and we'll hit flows, and then we'll do the next round of Q&A.
Perfect. All right. So let me. All right. So in the first 30 minutes, we introduced or reintroduced coroutines, right? We laid the groundwork for how channels and flows are going to work, and really broadly how coroutine backed solutions work in Kotlin. They all they all tend to follow some of these same patterns, these ideas like structure, concurrency, and use some similar syntax. Now, flows will also use a similar syntax to channels, but they work in a subtly different way. All right, flows are used to represent non-blocking streams. So if you use sequences in Kotlin, the syntax is going to be very familiar to you. All right, the problem, or rather the difference between flows and sequences is that if you're doing some long running work in a sequence, that sequence could block your thread. Now, flows are more explicitly used for long running work that you don't want to block. They are cold, meaning that they're not actually going to execute what's in the flow builder until they're actually subscribed to, or rather consumed. And they have a similar syntax to what you saw with channels. Whereas channels had functions with the names send and receive, flows have functions with the names emit and collect. Now, flows are most often compared to RxJava. So what we'll do is we'll first introduce the concept of flows, and then we will spend probably about the second half, maybe the second 20 minutes, comparing flows in RxJava and talking a bit more about the flow syntax in the lens of RxJava, because that might be a common domain for some people who have been using RxJava for years now and have heard about this new thing and want to know what it's all about. So we create a flow using a flow builder. Now, oftentimes, your flow is dealing with data that's already extant, right? You have a list of strings, and you want that list of strings to be represented as a flow, right? You want to take a list of strings and get out of it a non-blocking stream of strings. So there are flow builders like flow of, which takes in a variable number of arguments of really whatever you want to provide it. And then as flow, which takes in some collection, some iterable, and returns a flow out of it. You're good to go. You have a flow that you can now work with, just like really any other stream, except this flow is non-blocking and it's built on top of coroutines. So oftentimes, when our data set is finite, right, and let's say we just have some strings or some ints or even some custom types of objects, and we're not waiting for future emissions in the future, we can use one of these flow builders to really easily convert to a flow. But if we want to, I'll say, be a bit more custom, get a bit more granular in how our flow is created, we'll use a flow builder, all right, like a flow builder like this flow function. And that should specify as flow and flow of are themselves flow builders, but this flow function allows us to build a flow from scratch. So let's say that we have this numbers flow, and we're gonna do like a prime number example. So to start out here, we're just gonna take the number 3, emit that into the flow, and then while true, just emit one number after the other ascending indefinitely, right? Maybe we wouldn't use while true in production, but for the example, bear with me. We're just going to emit one number after another into this stream. All right. So I mentioned before, like channels have the send function and the receive function, a flow is going to have the emit function and the collect function. So this collect function is what's called a terminal event. So none of this, none of the code in the flow builder, none of the operators between the flow builder and the terminal event, this collect function, none of it is actually executed until that terminal event is fired. Okay, and that's part of this idea of flows being cold most often. Okay, so in order for a flow builder and in order for its code to actually be processed, you need some sort of terminal event. Without that, cool, you've built a stream, but you're not actually doing with it, and as a result, there's not going to actually be anything published into that stream itself. So you need a terminal event. So we saw emitting, we saw collecting, and then the third part of the Flow API is extending the Flow API. There are a whole host of operators that we can use to extend the Flow API, just like RxJava operators. And it's actually a bit simpler to extend Flow, in my opinion, than it is to extend RxJava. All that we need to do is create an extension function or some form of extension onto the existing Flow API. So let's say that we have a bunch of numbers and we want to filter out the numbers that are below the freezing point Kelvin. Okay, we can take our flow, transform it in some way, emit numbers in that stream, and return out a new flow. Okay, so there are built-in operators that you'll probably be familiar with from other contexts like map and filter and reduce. All right, those are all here. But if you want to create your own, you can just create extensions on top of that existing Flow API. Now here we're just extending specifically flows of integers, but you can have generic flow extensions as well, and they work just the same. So I want to step back and you'll see here that we've got our flow, our numbers flow, which was built. We've got filters. We can have some maps in here. You can see why people compare Flow to RxJava. And in part, that's because Android developers often come from object-oriented backgrounds. And so RxJava, this kind of injection of functional reactive programming sticks out in the code base. I won't say like a sore thumb, but it's noticeable. It has a very different style from the rest of your code. And you see that style here as well. So with flows, we can take things that are emitted into the stream, process them, right, with maps and filters and reduces, all right? And then we have some terminal event at the end that triggers everything, all right? A function like collect. There are other terminal events like toList that basically just collects everything into the stream and it returns a nice list for you. All right, but that's our core concepts: emitting, modifying in some way using operators, and then collecting at the end. Flows are great for solving problems like the one that we kind of hint at here on this slide. If we have a set of numbers starting at 3 and just increasing indefinitely, and we want to filter out prime numbers and we want to take the first 1,000 primes, that's really easy to do with flows, right? We just add this filter to filter numbers that are prime. We take 1,000 of those, and then when we collect, we want to actually just print out those numbers. So this syntax makes sense for flows in the way that it made sense for RxJava. Again, this will feel fairly familiar if you've used sequences in Kotlin. This is just a way to do so in a way that suspends. So that's the Flow API in about as much detail as we went into the channel API. From here, I want to talk about RxJava. And I want to talk about RxJava as compared to Flow. So why would we migrate away from RxJava? Right? RxJava has done this well for a while. but you've started to see more and more people talking about moving away from it. All right, we use it extensively at Big Nerd Ranch, right? We have for a while, but we are starting to ask, some of the same questions that other people are. Now, what problems do people have with RxJava? It's got a fairly steep learning curve. It's a learning curve that for a while, when people asked, can I have my Java developers start to write Kotlin code? Can I introduce Kotlin into my code base? It seems like a pretty big mental hurdle to move from Java to Kotlin. And my answer to that was always, well, you have them writing RxJava code, so they've already, gone and made, I'll say, like probably a more difficult transition, thinking about things in an object-oriented way versus a functional reactive way. That's one reason why we might move away from RxJava, because it takes a lot to onboard a new engineer into writing RxJava code compared to the object-oriented code that they may have been writing before. It's an additional dependency. I don't think that's a huge deal. We have lots of dependencies in our code, although it should be said that flows are a bit more baked into the Kotlin programming language than RxJava is into the Java programming language. That's not a huge biggie. I'll say lastly, RxJava has a fairly inflexible structure. You kind of do have to opt into its way of thinking and jump through a lot of hoops into fitting into RxJava's stream model, right? You spend a fair amount of time converting between different observable source types if you're using RxJava 2, right? If you've ever spent time converting from an observable to a single to a maybe to a flowable, then you'll know some of that pain. And then once you want to actually get that data out on the other side and do something with it, you're playing by RxJava's rules. And when you're using flows, because flows are built on top of coroutines, and they play by the same rules that are laid out in structured concurrency, you end up with a simpler syntax when you're trying to get your work, from a background thread back to the main thread, for example. So you'll see that the syntax is quite a bit simpler, at least quite a bit more concise when using flows versus RxJava. The last reason why we might migrate away from RxJava is one that I didn't actually mention on the slides here, but for so long, so many Android developers were kind of stuck with Java 7, right? They didn't have really good stream support like we got in Java 8. And what that meant is that we often found ourselves using RxJava to create a stream, just a simple stream. And that meant that we would spin up an entire new thread. Hopefully it was in a shared thread pool, but sometimes it wasn't. We would spin up a whole new thread just to do some simple piece of work that lent itself to a functional reactive way of thinking, but didn't actually need a whole new thread, right? So because Kotlin has a really great collections API and has support for this stream way of thinking, we don't have to opt for this like RxJava hammer for like what is a fairly relatively small nail, which is spinning up a stream. That said, even though I spent 3 or so minutes talking about why we might move away from RxJava, it is still a tool that's going to be quite useful for teams for some time to come. So I don't want to disparage it entirely because it has done us well. So RxJava in practice. From here, I want to look at some of the flow syntax and then call back to RxJava. All right, we'll talk about how flows compare to some of the different observable source types. We'll talk about the closest comparisons to those on error, on complete, and on next functions in a RxJava subscriber. And then we'll also talk about concurrency and how that works for a flow at the end. First, something I did want to clarify, and something that I've even kind of fallen into here, is comparing flows and RxJava as a one-to-one, right? We're just going to rip out RxJava and we're going to replace everything that we do with flows one-to-one. And this is something that I think it makes sense that we hear it quite often because it's a really simple comparison. Flows are really great for doing the same things that RxJava's observables and flowables do. But they're often unnecessary for singles, maybes, completables, right? Those RxJava observable source types that just return one or even zero things. In those cases, we can often just use suspending functions, and we end up with a lot simpler syntax in those cases, right? So I want to clarify that we shouldn't use flows to replace every single thing that we do in RxJava, right? You can. We showed off on a couple slides before a flow that emitted integers one after the other. But if we have a flow that just emits one integer, then maybe we don't need a flow in the first case, and we can just use a simple suspending function that returns an integer at a later point in time. So let's talk about error handling with flows. We'll talk about how the flow syntax compares to RxJava's onError function. And there are a couple different ways that we can handle errors using flows. And there are a couple different ways that we can handle completions in flows as well. So first, error handling. Because we opted into RxJava before, and let's assume that we're in some existing code base that contains RxJava code, and we've been working with it, and we're fairly happy with it, but we want to branch out. We trained ourselves to think in this functional reactive style, right? So every single thing has to be an operator. And I think sometimes what that leads us to is forgetting some of the language constructs that do exactly what we want to do, but are just kind of like simple or boring or rote even. So if we want to handle errors, like let's say we have a flow, and in that flow builder, we do some dangerous operation, and then we do something else in a map function, and we're at risk of throwing an exception here. We can just wrap that entire flow collection in a try catch, right? Now here, we're catching any exception that we could want to, right? Of course, we want to be a bit more specific. Maybe we're looking for IO exceptions or something like that. But here we're just catching any sort of exception, and we'll handle it from there. So we can use a traditional try catch like this if we'd like to, and that works perfectly well. We can also use the catch operator, and that catch operator feels a bit closer to that onError function that we used before. And if you want to have nice, pretty imperative-looking streams that look like this, the catch operator fits into that pattern really nicely. Okay, I tend to like the catch operator. It is experimental. All right, so like I mentioned before, a lot of the stuff that we'll talk about with flows, especially from here until the end of the session, a lot of these APIs are still experimental. So if you want to use the catch operator, well, that's going to require you to slap a @experimental coroutines API onto whatever scope you're using that thing in, or you can deal with the linter, or you can just ignore it, or I'm sure someone has built some broader solution to ignore the annotation. That said, it is useful to know exactly what you're doing and know precisely that the code that you're calling into could change at a moment's notice, and that you kind of are on the bleeding edge a bit. So 2 ways to handle errors in flows, right? You could just use a traditional try catch, like you might be familiar with if you're handling any sort of exception in any other code, or you can use the catch operator, which really has the same effect. So that's how flow syntax compares to onError. Now, completion. All right, let's say that we have some completion event when our flow is done emitting, and we want to have some code execute when we've handled all of the emissions in that stream. Well, again, we can go back to our trusty try catch friend and just add a finally block onto the end. Okay. Finally, once every emission has been collected, in this case, we'll just print out the string all done. Now, as we saw for handling errors, we can just use this new on completion operator. Okay, again, experimental, but it does fit into our stream pattern quite nicely. So that's flow completion. All right, that's our closest analog to on complete. Now, the last of these analogs that I wanted to talk about was on next. And this is a case that you can maybe potentially get yourself into trouble. If we want to have some side effect that, some piece of code that's called for each emission in the stream, we have the on each operator. But I want to clarify here that on each is not a terminal event. So you still do need to call collect on your flow in order for that flow's code to be executed. All right. So on each behaves similar to RxJava's on next, but you still do need to call collect because remember, you have to have some form of terminal event, whether it's a call to the collect function, maybe it's a call to a function like toList that returns you a nice collection at the end. All right, on next works kind of the same way, but this is something that you should look out for, or maybe you'll find yourself in a situation in which you call on each, you expect some code to be executed, and nothing's been executed because you haven't collected your flow yet. So that was on error, on complete, and on next. All right, those subscriber functions that you may be used to. Let's talk about execution context. And this is a really important way that I'll say helps the flow syntax and the flow API be a bit simpler than RxJava's syntax. Let's think back to structured concurrency. We create, we launch coroutines into a specific coroutine scope, and we manage that scope collectively. We manage all of the coroutines in that scope as one, and we'll often tie that scope to some resources in Android. Maybe it's a view model, maybe it's a fragment, something like that. So execution context. Flows operate in the coroutine context from which they're called. And we have an operator that we can use to change which dispatcher that we're using. So in this case, let's say that we are launching or rather collecting a flow on the main thread. All right, you can see here, using with context, we're specifying that this code should execute on the main thread. We call collect on a flow, and we print out whatever we collect, whatever emissions we collect. So this means that because we collect the flow on the main thread, everything in that flow, all the way back to the flow builder itself, is going to be called on the main thread. If we want to change that, if we want to specify that we want the contents of the flow builder to be called on some background thread, like something from dispatchers.io, then we can use this flow on operator, and flow on will affect everything above it in that stream. Okay, so we could, if we wanted to, have multiple calls to flow on at different places in that stream. All right, maybe we wanted to do a couple maps, a filter, and have them jump between different dispatchers, between different thread pools. Then we can do that with multiple calls to flow on. But more often, we'll find ourselves using a pattern like this, where we want to return the results of the stream. We want to take what we collect and then use it to update the user interface. Okay, so we want our long-running work. We want the what's being done in that flow. We want that to happen on a background thread because maybe we're going to the disk or we're making a network request. But when we're done, when we collect, we want to update the UI with our results. And here's how we would do that, right? We're updating or we're collecting on the main thread because our collect function was called from within this with context block. And that with context block specifies the main dispatcher. Now, there are other similarities between RxJava and the Flow API. One example is flat mapping. All right, flat maps work fairly similarly. Let's say that you have a flow that contains emissions of type flow, and you want to unwrap a kind of layer of flow from that. There are flat maps here, just like there is in RxJava. Let's say you want to take two flows and zip them together, right? Or combine the contents of those two flows into some new flow, right? Those exist here in the Flow API in a similar way as they did in the RxJava API, but perhaps a bit more, well, in a bit simpler fashion, right? The API is a bit more sparse, okay? So I say here, smaller API coverage and simpler syntax, those are by design, right? One aspect of the RxJava API, especially now with RxJava 3, is that over time, the number of operators in RxJava has grown really, really large. And so much of what is accomplished using those RxJava operators, we can just do in Kotlin because it's part of the Kotlin collections API. And we don't need those duplicate parts of the API in RxJava operators. So there are flow operators, but there are fewer of them, and that's by design to try and keep flow a bit simpler and let the rest of the Kotlin programming language, kind of do the rest of the heavy lifting in terms of API coverage there. The other difference here, and this might be evident at this point, but flows are entirely backed by coroutines. Okay, they're built into the flow syntax. They're part of defining how flows work, right? Flows work on top of coroutines, and as a result, because we're kind of opting in entirely to this coroutine pattern, we have a much simpler syntax as a result. Lastly, flows are going to be good for you if you are in a Kotlin only or at least Kotlin majority code base. There are ways to interface between flows and other domains. One example is RxJava. Kotlin X coroutines RX2 is a library that you can use to interface with the rest of your RxJava code. So it includes extensions like asFlow on top of some of those observable source types like observable and flowable and things that you're used to using from RxJava. So you can migrate gradually from RxJava to Flow by just converting from one to another using these extensions. You can also convert between flow types and I'll say like futures or other callbacks, maybe code that's defined in Java using extensions to the Flow API. All right, so it's not something where you have to be 100% bought into Kotlin across your code base in order to start using Flow. But I will say, if your code base is 20% Kotlin and 80% Java right now, then moving to flows at this point in time might be a little bit premature. You might want to prioritize the rest of your migration from Kotlin to Java first, because you'll end up jumping through what I would deem as too many hoops in order to best support your flow code. So let's wrap things up here. Channels versus flows. All right, we've grouped them together. Sometimes you'll see them grouped together, but I do want to make sure that we clarify the differences between the two. Channels are just a pipeline that coroutines can share. All right, multiple coroutines can produce emissions into that channel stream, and multiple coroutines can potentially receive from that channel. And there are different types of channels that work best for each of those different permutations of, I'll say, a number of consumers, number of producers, and then the behavior of the channel they're in. Okay, so channels, just a pipeline for coroutines to communicate with one another. Flows represent individual streams. They're not as often used as pipelines in this way, but that is something that is kind of being called into question. If we look forward to the future of flows, if you're curious, I'll encourage you to look at this particular issue in the coroutines issues list, right? It's the introduction of an API called shared flow, all right? And shared flow, well, I'll say it starts to bend and maybe break some of the rules that I introduced here. I mentioned that flows were cold, and shared flows introduce the idea of a hot flow, right? Shared flows aim to replace broadcast channels, a type of channel that I explicitly didn't talk about because it's being reproduced, or I'll say re-implemented here. Flows are starting to encroach on some of the work that channels did before. So when we talk about the difference between channels and flows, there was a pretty clear answer until 10 days ago, and I had to rewrite the end of this presentation. But if you're curious about the future of flows, what you can do with flows, and some of the things that JetBrains intends to do with the Flow API going forward, take a look at this introduce shared flow issue on the coroutines repo. There's lots of really cool stuff in there. With that said, we are right at time. Thank you so much for being here today. As a reminder, my name is David. You can follow me on Twitter, always looking for cloud. If you have questions about channels, flows, let me know in the Q&A session. Otherwise, thank you so much to droidCon. This was a tremendous opportunity and loved getting a chance to talk to you all.
Thanks, David, so much. I enjoyed the heck out of that presentation, learned an awful lot. It's always great. And again, you guys from Big Nerd Ranch always do such an outstanding job. We can always tell just you guys are very professional about the way you do this. So we're grateful to have you with us. We've made Uli the moderator again, and he should be sharing his screen because I know we do have a number of questions. So I'm going to let you dive into that, okay?
For sure. So, all right, why the question, dispatcher default cross async task? I'm not sure I fully understand the top question. I saw that come in at the very end of the last Q&A session, and I'm not sure I fully understand what's being asked there. So if we could maybe get a clarifier, I'd appreciate that so I can address it. So the next top question here, when will we use flows over channels? Really, so if you have experience with RxJava in the past, there's, well, it becomes a bit easier to answer this question because there's a kind of a clear comparison between channels are like subjects, meaning that you can produce and consume to this stream that exists outside of your other coroutines. And then flows are a bit more like the other observable source types. They just represent a stream like an observable or a flowable or something like that. So if you don't need some of that, well, if you don't need to be able to produce to a channel and consume from that channel, that's when I would opt for a flow. In part because under the hood, the flow implementation, it's a bit more performant, right? Channels do a bit more work. As such, you might, in your particular case, might vary, but you might find that flows are a little bit more performant than channels. Can you do a quick summary of what you mean by hot versus cold? Sure. So hot versus cold, this is an idea that personally was introduced to me in the context of observables in RxJava. Simply, something that is hot is going to produce no matter if there are consumers for it, right? So if we have a channel and we're sending things into that channel, we can keep sending things to that channel, right? Even if no one is receiving it, okay? Nothing is stopping us from executing code in a channel builder or a producer just because no one is consuming it. Now, something that is cold means that code in a flow builder, for example, using an example of a cold flow, that code's not going to be executed until that flow is eventually collected, okay? So that's, I'll say in terms of your performance, there might be some subtle differences there, but it's the execution of the code in a channel implementation and the way that, I'll say execution flows through a channel is going to behave very differently because of the differences between hot and cold streams. So can channels and coroutines replace all usage of RxJava? Eventually, yes. This is a very open-ended question because you could create a competitor to RxJava today and eventually replace it entirely. It's going to take some time though, and flows get us a good amount of the way there. There isn't a one-to-one mapping just yet in the Flow API that takes care of everything that RxJava does, and there likely won't ever be by design. But the idea behind the implementation of the Flow API is to give you the basics, give you the fundamentals, the tools that you need to represent streams and modify the contents of those streams in flight. And then just make it a really easy API to extend. So anything that you're missing that you used in RxJava that you don't find in the Flow API, you can more easily just reproduce that by kind of writing it yourself. I do want to clarify though that sometimes I do see people just say like, oh, it's fairly straightforward to just write this yourself. This thing that you were using and you were happy using, just implement it yourself. It's easy. It's not always easy, but fortunately we have a great community in the Kotlin community and in the Android community where people are experimenting with the Flow API. It's in really active development right now. So there are lots of people that can help you get to where you want to go. You can bounce your ideas off of them, pair, program, and get to where you were with RxJava fairly quickly. Can you have multiple users of a channel? Yes, and there are two ways to answer this. One is that yes, you can have multiple producers sending things into a channel, right? You can also have multiple consumers of that channel if you want to. All right, so you could have multiple receivers pulling things out of that channel and processing those emissions in turn. So yes. If you collect a flow, does this need to be disposed of when you're done observing it? So this was something that, well, I talked about the execution context of a flow, but I wasn't really as explicit about how a flow is cleaned up. The thing that a flow gives you that just like a normal suspending function doesn't give you out of the box is this assumption that your flow is going to execute in the scope in which it's called. So if you've opted into structured concurrency, right? If you are managing your coroutine scope, we just had a power flicker, hopefully we're still online. So if you've opted into structured concurrency, if you're managing your coroutine scopes, then your flow is, it'll be disposed of when your coroutine scope is disposed of as well. That said, famous last words, and there are all sorts of nuances there. How would you stop X different coroutines if any one of them is finished? I'll say you would most often, if you had a set of coroutines of X different coroutines that you wanted to treat collectively, you would likely treat them as a scope. Maybe there's not an example that I'm thinking of here where you had a bunch of different coroutines in different scopes, but it's, I would say, more common, maybe even more technically correct, to treat scopes and treat, we'll say, jobs collectively rather than individual coroutines collectively. So if you wanted to do something with all of the coroutines in one particular scope, then that's fairly straightforward on the job API, right? You can check if a job is active, you can cancel a job explicitly, etc. Does launching in viewModel scope work in an activity or fragment that uses a viewModel, or should it be reserved for use only internally in a viewModel class? Activity or fragment that uses a viewModel. I'm not sure if I understand fully the question as written. You would reference a viewModel scope internally from within a Jetpack viewModel, right? And the code that I showed off on that particular slide, where we referenced that viewModel, that code was completed. It compiles. You're just grabbing the viewModel scope, which is exposed from that parent viewModel class. So you are doing so internally from within a view model, and to expose that view model scope outside of that class might be odd. Hopefully, I answered your question in full there. Performance comparison between RxJava and coroutines, for example, memory, CPU consumption, etc. Between the two, anything that you do in RxJava is more likely going to be influenced by the size or the number of emissions in your stream, what you're emitting, what sort of processing you're doing, right? Maybe you have something really complicated in a map that you're doing, and that's probably going to more often influence the performance of your RxJava code. But fundamentally, and why we might move away from RxJava is simply that a pattern that you'll see out there in the wild is people will use RxJava just to move work off to a background thread. And rather than using an existing thread pool, they'll just spin up a new thread to do whatever work that they want to do. So you'll see something like people taking some strings and getting the length of those strings, and we've spun up an entire new thread to do a really simple operation, right? So something that executes really quickly. And the advantage of coroutines is that we don't need to spin up a whole new thread to do so. We could use a coroutine that maybe uses an existing thread or is able to share that thread when it's done. So I'll say inherently, coroutines more often will be more performant because they're more performant than using threads directly. But that doesn't really answer every permutation of a question that you could have about RxJava, because it's really more important what you're doing in your RxJava streams. Asking for the other guy. Okay, so I see this is a clarification, I think, of the earlier question about async task thread pool dispatcher. I don't as often use async task thread pool dispatcher, so I don't know if I have a great answer for you that's going to answer all cases. What I do know is that the thread pool that async task uses has changed over time in Android. So that's something that that might vary based on which version of Android you're on, and really would vary based on the size of that thread pool. That said, because I don't use async task thread pool dispatcher very often, I don't have the exact answer that you're looking for. Do you mind if we keep going, or should we call it, or?
David, it's up to you. We've still got quite a few people in the room, and there's some questions coming. So I think we could probably let this go for another few minutes, and we'll end at 11:30 your time. Maybe about 7 more minutes if you're up for it. That'd be okay?
Sure. Yeah.
All right, let's crank away at these.
If you're answering, or if you're asking a question now, and we don't end up getting to it by, I guess, 7 minutes from now, feel free to reach out, Twitter, something like that. Feel free to ping me. Love to be able to get through everything, but it may not happen. Do I have to manage a coroutine in a way like shut down and unregister a coroutine? Well, there are a couple ways to look at that. One is, what's your coroutine doing? Are you grabbing a hold of some other resource, right? Are you creating are you opening a hook into a file, right? Are you making a web request? Because those are things that you want to manage independently. But going back to the idea of structured concurrency, that's what that whole idea is about, right? You're treating these collections of coroutines as one, and you're managing those collections of coroutines within scope kind of as one. So in the implementation of a coroutine scope, you'll actually see that explicit managing of those coroutines within a scope, right? Or really, the jobs themselves through that particular scope. So if you're creating your own coroutine, yes, you'll have to do that. Or sorry, if you're creating your own coroutine scope, yes, you'll have to do that. But more and more often, especially in the past year, more of the domains in which you use coroutines, people are writing coroutine scopes for. View model scope is a perfect example of this. Because that work is done for you, you don't have to explicitly think about it as much, and that's part of the, I'll say, the, you know, maybe a plus and a minus of coroutines. The syntax is really simple, deceptively so, because they're quite complex under the hood if you aren't explicitly familiar with what's going on. Coroutines are lifecycle aware. There is a lifecycle scope, like an explicit lifecycle aware coroutine scope that you can use that does exactly that, but nothing in the implementation of coroutines themselves is explicitly lifecycle aware. They're a Kotlin programming language construct. Nothing is prescriptive, about them working on Android. Although there are certain parts of the, like, the dispatcher API that nod to Android, like dispatchers.main, but coroutines themselves, they're part of the Kotlin programming language, and therefore are intended to be platform agnostic. Flow and channel use case in Android. So let's say that we have from a view model, right? We want to update our UI with some fresh results from the web. All right, so we call back into our backend, right, into our model. Maybe we have like a repository object if we're following the repository pattern, and we make a request to some remote web service. We want that work to be done on a background thread, and we want it to return to the main thread so that we can update our user interface, because we can only do so from the main or UI thread. All right. Now, the way that data flows from our web backend through our repository back into the view model, it's unidirectional, right? It flows in one direction. And as a result, it becomes really advantageous for us to think about the way that data flows in the form of a stream, right? It originates somewhere, we can make modifications to it along the way. And by the time it gets to where it needs to go, which is essentially our user interface, it's just a really straightforward way of thinking about that sort of that way of programming. So that's our key use case for flows. Now, channels would be probably a bit more useful back in our data backend, right? If we have multiple coroutines that are pulling data from multiple different sources, and we want to maybe merge that data together or update some other interested party, some other consumer, then a channel might be our best case for that. What's your take on RxJava subjects versus channels? Because some industry experts say that RxJava is still way more powerful, and yeah, that's apt, depending on your definition of powerful, right? RxJava has a way more extensive API. There's more that RxJava does out of the box, specifically in the subject API, than in Kotlin Coroutines channel API. And if API coverage is what you're looking for, then sure, go with RxJava, especially if the rest of your code base is already in RxJava and you've opted in to RxJava as a team. Subjects are going to be great for you. But if you want something that's backed by coroutines and is part of the coroutines API, channels are the way to go at this time. But again, depending on your definition of, depending on what your team values, depending on what you mean as like powerful, that can vary. Is there a recording of this session and also the previous session? Maybe that's a good question to end it on, and I'll pass it back.
Sure, I'm happy to take that one from you. Yeah, we had all the webinar recordings are online. In fact, just this session by David was a standalone session that was done as part of our Advanced Kotlin series, of which there will be 3 or 4 between we started in the April timeframe and going through September. The first ones, just so you know, were refactoring legacy code with Kotlin. We did some Kotlin scope and extension functions and the inline keywords. So that was the first one, but yes, that's a video that is available on droidcon.com as well, and all those are there. This one, of course, will also be available as well. All right,
Perfect.
great. David, thanks so much for being here. You're a real trooper. I really appreciate it. Just so you know, huge kudos to you from people in the audience. I've had a lot of private messages coming my way saying thank you so much for your presentation. It was outstanding, and for your knowledge and the depth that you brought to this topic. We really, really appreciate it. Thanks to you, and of course, thanks to our partners at Big Nerd Ranch as well for being a part of this. And I'm going to get my video on back here. Anyway, thanks so much again for everyone for logging in today for today's webinar. Remember, the next series starts again, the second part of our Jetpack series is June 11th. And again, check your chat function real quick, and also on my slides, it'll be on the video for some information about some more in-depth webinars and trainings coming up from our friends over at Big Nerd Ranch. We hope you'll take advantage of those. David, thanks again. Really appreciate it. We hope to have you back. Look forward to seeing you again in person at future droidcons as well.
Absolutely. Thank you so much.
All right, everyone. Have a great day. Stay safe. Stay healthy. Bye-bye.